Hello my dear students, am I audible and visible to you? Prerna Rajput, oh thank you. Alpha Kacha, how's your studies going on? Am I audible and visible to you? Well, it takes some time to initiate for me to check whether it is working actually or not. Hello? Yes. Am I audible? Yep, I am audible and visible, and we have wasted a little bit of time because I was not able to confirm whether it has started or not. So today we are going to talk about electrochemistry, and this chapter, when we talk about electrochemistry, is a very important chapter. It is a very high scoring chapter. Many questions come from this particular chapter in the NEET examination as far as your board examination are concerned. Again, this is a very important chapter. It has a huge Yep. So we are going to talk about from today onwards electrochemistry, which is we are going to talk about electrolytic conductance today. Now, this is one of the lengthiest chapter of chemistry. Yes, it is a very long chapter, and as far as I am concerned, I feel it's a bit difficult chapter also. So we are going to do this chapter very nicely, very slowly, thoroughly. And since I don't have many of the students in my class, so it is going to be a real one-to-one session where you can ask me all the doubts very clearly and I'll explain it to you according to you. Is it clear? Perfect. Naruto, your first class in Unacademy, welcome to this session, and I would request you to join my special class at 5:30 p.m. Today we are having a special class at 5:30 p.m. in which we are going to do all the questions of solution chapter. I have already included how many questions? I have included 30 plus 30, 60 questions. Today we are going to have 60 questions because most of the time what we find is that we have less number of questions and more number of answers. So today we are going to have huge number of questions. So be there at 5:30 p.m. in special class. Special class today you have to join on unacademy.com/Anoop Vashishtha. Is that clear? Okay, so today we are going to start with this chapter and a little bit about myself. You already know my name is Anoop Vashishtha. I am an MSc in chemistry from University of Delhi. 26 years teaching experience, lakhs of students have been taught by me, and I am here with you on this particular channel. So to begin over with the topic called electrochemistry. Now electrochemistry is a topic which is going to deal actually with 4 topics. There are not only 3 but there are 4 topics. One of them is redox reaction as well. We are not including redox reaction here because redox reaction is going to be the topic of 11th class. Here we have electrochemistry is the study of equilibrium and kinetic properties of ions in solution, production of electricity from the energy released during spontaneous chemical reaction, or its reverse, when electrical energy is used to bring about the non-spontaneous chemical reaction. So when we talk about this electrochemistry topic, just remember, when we talk about the equilibrium and kinetic properties of ions in solution, this becomes electrolytic conductance. Production of electrolysis is electrochemical cell. And when we talk about its reverse, this is what we call as electrolysis. So this becomes the sum total of electrolytic conductance, electrochemical cells, and electrolysis. We are going to talk today about electrolytic chemistry. Yeah, today is MCQ, beta Munna. At 5:30 we are going to have MCQs. And since we have Unacademy app with us, Unacademy app allows you to solve the question, take part in the quiz, and you are getting leaderboard as well. And you are going to get the PDF of those quizzes. You can download the PDF. I believe the previous classes, if you can go along with it, you just click on that previous class and you will get a choice to download the PDF in two forms. One is annotated, where whatever I have written is going to be there, and one is non-annotated, where you are going to get the PDF as it is. So you can download the PDF nicely. Is it clear? So this is going to deal with electrolytic conductance, that is the first part. Then we have electrolysis and we have electrochemical cells. That is what we also known as the galvanic cell. So now, to get along with the conductors, we are going to talk about electrolytic conductance. So before that, we get along with something called the conductors. I am going to do it in very much detail, and I am going to touch other topics as well. Please remember that I am not going to go out of your course. I'll stay within your course, but I am going to cover it thoroughly. Is it okay? Those who have not liked as yet, please like the session. That's great, Shakil. Yeah, Menti, it is better than Menti because you don't have to change the platforms. You are able to hear it, you are able to do it. Bapi, my son, he's preparing. Okay, so let's talk about something called conductors. The first one is what we know as the metallic conductors. Now, when we talk about the metallic conductors, we can also term them as electronic conductors, because in these cases, the charge carriers are electrons. You need to understand that the charge cannot flow on its own. Like energy can flow in the form of electricity, the light. Electromagnetic radiation can flow without the medium, but the charge somehow does not flow without some material particle associated with it. Some mass has to be associated with the charge. In case of electronic conductors, that is metals or semiconductors, the charge carriers are electrons. In case of metals and metal-like conductors, the electron are the charge carriers. Now, in the case of metals, as the temperature is increased, the vibration of the metallic kernels increase. Metallic kernels, what are these? Metallic kernels are metal atoms from which the outermost shell electrons have been removed. Shakil, please understand, I am not talking about materials that allow the electricity to flow from them easily. Those are agreed conductors. What I am talking about is that charge is associated with the material particles. Charge cannot flow in absence of any mass. Charge is always associated with some mass. Is that clear? So, as the temperature is increased, the vibration of the metallic kernels increases. This resists the flow of electron and decreases the conductance. So, in the case of metals, with increase in temperature, the conductance decreases. Now, with decrease in temperature, the conductivity of the metal actually increases, and certain metals like mercury become superconductors near absolute zero. Superconductors are those that if you allow the electric current to flow through them, it will keep on flowing forever. That's what it becomes, superconductors. Fine. Now, electronic conductance depends on what are the factors? I have already told the nature and the structure of metal, the number of valence electrons per atom, the density of the metals, and temperature. So, these are the factors which are going to affect the conductance of the metals. As the electrons enter at one end, go out of the other end, the composition of the metallic conductor remains unchanged. So, by passing of the electric current, the metallic conductor does not change. That is why the wires keep on remaining there for a very long time in your house. The wire composition does not change. Is this clear? Yes, BDS is a good one. Okay. Now, resistance to current flow in a metal is caused by the vibration of the metal ions about their lattice position. Such vibration interfere, now only I told you, metallic kernels, and consequently retard the flow of current. On increasing the temperature, the thermal motion of the metal ions increases and thus offers more resistance against the flow of electrons, and the metal become poorer conductor will rise in the temperature. I have told you one thing only in multiple ways. But why metals like mercury? This is not the topic of discussion in this particular chapter. We can only say that the mercury and these metals like lead, which are not very good conductors of electricity, they only become the superconductors. Perhaps they show a larger change with temperature. Okay. So, this is what we have as the comparison. We have metallic conductors, we have electrolytic conductors. In the case of metals, the charge carriers are electrons. In the case of electrolytic conductors, the charge carriers are ions, that is cations and anions. In case of metallic conductors, if we conduct electricity, there is no chemical changes. In case of electrolytic conductors, the decomposition of electrolytes can take place. It's not a necessity that it will take place, but it can take place. So, we have when we have increase in temperature, the electrolytic conduction increases, and electronic metallic conductors conduction decreases. The electrolytic conduction increases. So, metallic conduction depends on the nature of metals, electrolytic conduction depends on the nature of the electrolyte. Clear? So, that is what we have already understood. So, in case of metallic conductors, there is no transfer of mass, but in electrolytic conductors, there is actually a transfer of mass. The mass actually moves from one electrode to another. Resistance is due to the collision of electron with fixed metal atoms. Resistance is because of the collision of ions with solvent molecules and because of inter-ionic force of attraction. Clear? So, here we have the metallic conductors. When we talk about the metallic conductors, this is a metal rod. Here we have the length L, and here it is the cross-sectional area. We can even have something like a rectangular piece or cuboidal piece. This kind of a metallic conductor, and in this kind of metallic conductor, this would be the area of cross section. This is what we have as A, and this is the length of the conductor L. Is that clear? So, in case of metallic conductors, finding out the length of the conductor and the area of cross section is extremely easy. And then they're fine enough. But actually, I am repeating the things again and again, so I believe that should be okay. Okay, now let's talk about something called the semiconductors. Semiconductors have a conductance in between the insulators and conductors. Now, what happens in the case of semiconductor? In case of semiconductor, we have something called the band theory. What is the band theory? We have here the valence band, we have here conduction band, and this is what we call as the forbidden gap. The valence band consists of electrons. The conduction band consists of holes. Some of the electrons from the valence band move over to the conduction band by absorbing some energy, and thus some vacancy is created in the valence band while electron moves into the conduction band. Because of the vacancy, the electron can flow in the valence band, and because of the electron, they can flow in the conduction band. And that is how the semiconductors are able to conduct electricity. Is it clear? Ananya, are you able to understand it now? Teethraj, I could not understand. What do you mean by less than, greater than? Fine. Now, one thing you need to understand that as the temperature increases, more and more electrons, they shift from the valence band to the conduction band. And if more and more electrons are able to shift from the valence band to the conduction band, the electric conductance of a semiconductor actually increases with temperature. So, the semiconductors, the band width, Tirthraj, fun fact, I am with you. So, which company I am with, how does it make a difference? Or you are advocating a particular company? Okay? Please don't spam. Fine. So, the electrons, they move more and more as the temperature increases. But the problem with the semiconductors is that if we sufficiently increase the temperature, the conduction will only increase to a certain limit. It is not going to become a superconductor by increasing the temperature. The reason is straightforward, because at a very high temperature, the electrons actually, when they move up, the semiconductor is going to melt, it is going to get decomposed. So, that is why a semiconductor does not become a superconductor with increase in temperature. Okay? With increase in temperature, more electrons move from the valence band to the conduction band, increasing the conductance. Clear? This movement decreases the bond strength, and hence a semiconductor cannot be made a superconductor by increasing the temperature. Now, we have the definition of something called electrolyte. Now, when we talk about the definition of the electrolyte, we actually have one common definition and one specific definition for this particular chapter. Now, electrolyte is a species which dissociates into ions and conducts electricity when molten or in solution. So, that's what we have as an electrolyte. For this particular chapter, we are going to simply consider the electrolyte as a species which dissociates into ions and conducts electricity in water as the solvent. Is it clear? Yes, fun facts, this is the complete English channel, and I hope I am not speaking that difficult English that you will not be able to understand. Yes, Prerna, you just need to type Anoop Sir, and you are going to get the classes of every topic in chemistry on perhaps every platform. Okay? Clear? Whoever has not liked the session as yet, quickly like it. So, that's what we have as electrolyte. So, electrolyte are the species which dissociate into ions and conduct electricity when dissolved in water. Now, electrolyte has ions, that is cations and anions. Now, as we increase the temperature, the dissociation of the electrolyte actually increases. Now, if the dissociation of the electrolyte increases, the number of ions are going to increase, and similarly the conduction is going to increase. What is electrolytic conductance dependent on? Is sugar an electrolyte? No. Sakil, Shakil, sugar is not an electrolyte. Clear? Clear? Now, the conductivity of the electrolyte ionic solution depends on the nature of the electrolytes added, quite obviously, the size of the ions produced and their solvation. Peculiarly, the solvation is inversely dependent on size. More is the size of the ion, it has lower solvation, and smaller is the ion, it has the higher solvation. What we are concerned in the case of electrolyte is not the ion but the solvated ion. So what matters is not the size of the ion, but the size of the solvated ion that matters. Yes, Devansh, I am going to teach you entire chemistry. The nature of the solvent and its viscosity. If you change the solvent, then in that case the dissociation is also going to change, and even the movement of the ions is going to change. Concentration of the electrolyte, quite obviously. Temperature, now it increases with the increase in temperature. But in case of electrolytes also, you cannot make the conduction as infinity with increase in temperature, because at a certain temperature the electrolyte solution is going to start boiling, and when it boils, the solvent is going to get evaporated, and so it is not going to become a superconductor. Further, there is a limit to which you can increase the temperature of an electrolyte. Is this clear? Munna Kumar, what I am teaching is, I am writing the main points. It is already written, and further these things are to be understood. You are not understanding the subject to become teachers. You are understanding the subject so that you are able to give the right answers. And to give the right answer, you just need to hear it. You don't need to actually learn it. Okay? These are the points which are important. So what I am telling is to explain these points. Okay. Now, when we talk about electrolytes, we talk about some current. We have the direct current, we have the alternating current. If we pass the direct current through the ionic solution over a prolonged period, it can lead to the change in its composition due to electrochemical reactions. So, if we have the electrolyte solution and we pass direct current through it, it can lead to a change in its composition. Okay. So, what we have understood is electrolyte by definition are substances which dissociate into ions when in solution. The movement of the ions gives rise to what is known as electrolytic conductance. It depends on the mobility of ions, how easily the ions can travel, and anything that inhibits the motion of ions causes resistance to current flow. I hope this is not confusing. So, what I had explained, the same thing is written right here. So, conduction is exhibited principally by molten salts and by aqueous solution of electrolytes. The solid salts like sodium chloride in the solid state is not a good conductor of electricity. Is this clear? Now, these are the factors that influence the electrical conductivity of solutions of electrolytes include interionic attraction, solvation of ions, viscosity of the solvent, and these factors depend on the attraction of the solute-solvent and solvent-solvent respectively. So, it all depends on these interactions. So, I have reaffirmed what I have already told. Okay. Now, I told you that as the temperature increases, the electrolytic conductance increases. Why does it increase? The average kinetic energy of the solute ions increases as the temperature is raised, and therefore the resistance of the electrolytic conductors generally decreases. Remember, resistance decreases, so the conduction increases as the temperature is raised. Any kind of confusions? Now we have a definition called strong electrolyte. The strong electrolyte types. The substance which completely dissociates into ions. See, this particular word is going to be used many a times in this particular chapter, even in the equilibrium chapter. So, this word you need to understand. So, strong electrolyte is the substance which completely dissociates into ions when dissolved in water they are termed as strong electrolytes. Now, many a times we say that all strong acids are strong electrolytes. No. The strong electrolytes which give H plus ions are termed as strong acids. Okay. So, every strong acid is going to be strong because it's a strong electrolyte. In the same manner, all the strong bases are strong electrolytes. And further, all the salts, they are strong electrolytes. The salts might not be soluble in water, that's one thing, but whatever dissolves in water is completely dissociated. So, by that definition, the salts are all strong electrolytes. The substance which dissociates only partially in water, they are termed as weak electrolytes. Now, examples obviously are weak acids, weak bases, and most important, water. Water is a weak electrolyte. Any confusions, anybody? Clear? So, the electrolyte conduction increases with temperature. Now, we have something called the Ohm's law. Ohm's law says it is metallic as well as electrolytic, they all obey Ohm's law, which states the strength of current flowing through a conductor is directly proportional to the potential difference applied across the conductor and is inversely proportional to the resistance of the conductor. That is, I is proportional to V and I is proportional to 1 by R. In fact, I is equal to V by R. Tirthraj, I prefer to write I is equal to V by R because current is proportional to potential. It's not other way around. Voltage, the potential is not proportional to current. Clear? Okay, so that's what we have as mathematical representation of the Ohm's law. The current strength is measured in amperes, the electrical resistance is measured in ohms, and potential difference is measured in volts. So, these are the units of these quantities. Now, when we talk about chemistry, instead of resistance, we prefer to use the term conductance, and NCERT has used the symbol G for conductance. Why it is Z? It is G. This term implies the ease with which the current flows through a conductor. I simply don't know that if we make a bridge over a river, then in that case, the people will be able to cross the river. Should we say that how much the bridge resists the movement of the people because only a certain number of people will be able to move through the bridge, or it conducts the people? So, in chemistry, we prefer to call about conductance. In physics, they talk about resistance. They would say that a bridge resists the movement of people because it's not allowing all the people to move at the same time. The chemistry people say it allows some people to move through, so it is conducting the people. It's the way how we look at it. Clear? So, this is what we have as conductance. It is defined as reciprocal of resistance. It's 1 by R, and it is can be represented in a unit called reciprocal ohm or Ohm's inverse. We can call it Ohm inverse. Certain people even call it MHO, that is, you have inversed the word, and the symbol we can use as Ohm inverse, and some people even reverse it. And now, if you are going to reverse it, then in that case there is not going to be any minus. So, all these are the ways to represent it. But if we talk about the SI unit, that is Siemens. So if anybody asks you the SI unit of conductance, it is not ohm inverse, it is Siemens. Any confusions? So remember, at 5:30 we are having the questions of the chapter called solutions. So this is what we have as R is proportional to L by A. The resistance, when we talk about resistance, that is equal to rho L by A. More is the length of the conductor, more is the resistance. More is the area of cross section, less becomes the resistance. Many times when you talk about the current flow, and remember the word current itself has come from the flow of water. So whenever we are talking about the current flow, we can always relate it to the flow of water, and these conductors or resistors can be considered as water pipes. Longer is the water pipe, slower will the flow of water become, and thicker is the water pipe, more water is capable of flowing. Is that clear? So, as the area of cross section increases, the resistance decreases. As the length increases, the resistance increases. And rho is what we call as resistivity. Nowadays, the word which is used is resistivity only. Earlier it was called specific resistance. Still, if you use specific resistance, nobody is going to cut the marks, but resistivity is what is suggested. Clear? So resistivity is a solution defined as the resistance of the solution between two electrodes of 1 centimeter square, area of cross section 1 centimeter, or it is resistivity is the resistance of 1 unit cube of the conductor. So resistivity rho is resistance of a unit cube of the conductor. Is that clear? So if you talk about the units of resistivity, see, resistivity is, we have R is equal to rho L by A. Now R unit is ohm. Resistivity unit we need to find. Length unit is any of the length unit, let's say meters. Area unit would be meter square. So if I talk about the unit of rho, that is going to be ohm meter inverse. We are going to change the unit of length, then in that case it becomes ohm centimeter inverse. So that is the unit of resistivity. Clear? Oh, ohm not inverse. It is going to be meter. Is that clear? Because it's going to be rho by m, ohm into m. Clear? So inverse of resistance is what we call as conductance. So if you talk about G is equal to 1 by R, so G is equal to 1 by R, that is equal to 1 by rho into A by L. Clear? And the units of conductance we have already done. Ananya, the resistance of any conductor varies directly as its length and inversely as its cross-sectional area A, that is rho is proportional to L by A. Clear? So specific resistance or resistivity is defined as the resistance in ohms of a specimen 1 centimeter in length and 1 square centimeter in cross section. It is the resistance of 1 centimeter cube of the material. Shivanshu Mishra, if you feel that teaching is so easy, why don't you prepare the slides and start teaching? Easy? No extra effort. Let's see you teaching. Then we are going to decide whether it is extra effort or not. If you feel it is not an extra effort, then you are going to be extremely successful. Go ahead and do it. Okay? So 1 by rho, the inverse of resistivity, is called specific conductance, or we call it conductivity. Specific conductance is called conductivity. Okay. Now again, this is going to be the conductance of a cubic material of edge length unity. It is generally denoted by not K but kappa. Kappa is equal to 1 by rho. Rho is equal to A by L into R. So kappa is equal to 1 by rho, which is 1 L by A into 1 by R. So L by A into conductance, which is G. Anything you want to ask here? I hope I am not going too fast. If I am going too fast, you can just tell me. I will go slow. As Ananya said. Munna Kumar, what's the difference? Which difference are we talking about? जीते रहो बेटा शहादत हसन. Now conductance is measured in ohm inverse, length in centimeter and area in square centimeter. The units of specific conductance becomes ohm inverse centimeter inverse, or you may say ohm inverse meter inverse. And if you talk about this ohm inverse, we talk about Siemens, that becomes Siemens meter inverse. That is going to be the SI unit. The normal used is Siemens centimeter inverse. So these are the units of specific conductance or conductivity. You need to learn these units because they may be asked in the exam. Welcome Shahadat Hassan. Like the session. So this is what we have as the SI unit of specific conductance. Now, if we talk about the solution, the conductivity of a solution at any given concentration is the conductance of 1 unit volume of the solution kept between 2 platinum electrodes with unit area of cross section and a distance of unit length. Now, this unit could be meter, could be centimeter, or could be any unit which you prefer. Conductivity and conductance. Conductance is of the particular cell of particular electrolyte. But when we talk about conductivity, we define the length and the breadth. Conductance is of the system, conductivity is of a unit. Okay? Munna, is this clear? Conductivity is specific conductance for a given dimension. Now, when we talk about ionic solutions, ionic solution, when we talk about measuring the conductance or the resistance, there are 2 problems with that. First problem is that when we pass the direct current, it would change the composition of the electrolyte. So, direct current cannot be used to measure the conductance of the electrolytes. And then we are going to see the table, don't worry. All the tables are right here in this particular PPT. So, passing the direct current changes the composition of the solution, first thing. And further, and you cannot just connect the solution to an electrode. Like metals can be easily connected to any electrode or any wire, and we can measure the conductance of the metals. But for the electrolytes, we can't do that. Is this clear? So, that is the problem with the measuring of the conductance of the electrolytes. Now, first difficulty is resolved by using an alternating source. Whenever we talk about the electrolytes, the current which is used to measure the conductance of electrolytes is not the direct current, it is the alternating current. Have you noted it down? That we are going to use alternating current for measuring the conductance of the electrolyte solutions. And the second problem, we use something called a conductivity cell. Is that clear? Okay. So, here we have the same things which we have already done. Now, this is what we have as something called the conductivity cell. We are able to measure the conductance using it. So, here we have the electrodes. This is what we have as the electrode. Here we have the length between the two electrodes. Now, this length between the two electrodes becomes the L, and the area of the electrodes becomes A. So, these are the cells which are given in NCERT. The actual cell, when we talk about the conductivity cell, would be consisting of two platinum pieces, 1 centimeter square each in the area, which is fused in the glass. Here we have the distance as 1 centimeter. This is fused here. There are two silver wires which are moving through it. Now, whenever we are making such kind of instruments, the wires which are used are of silver. Why do we use the silver wire? Because this is the best conductor of electricity, and it does not become heated when current is passed through it. It's a cold conductor. Fine, it's a cold conductor. Now, the area of these plates is 1 centimeter square. Now, these electrodes, they are not simple platinum. These are platinized platinum electrodes. So, here we have L is equal to 1 centimeter, A is equal to 1 centimeter square. So, L by A simply comes out to be centimeter inverse or 1 centimeter inverse. Clear? So, this is what we call as conductivity cell, which has a L by A as 1. Now, this L and this A, they depend only on the container. The L and A, they do not change with the electrolyte, they do not change with the temperature, they do not change with the pressure, they only change with the container. If you change the container, L and A are going to change, but if you keep the same, they are going to remain the same. So, this is L and A are constants for the cell. So, this L by A is termed as the cell constant. L by A is termed as the cell constant. Fine. Now, cell constant in NCERT has been represented as G star. Are you clear? Why we have kept as L by A as a constant? Because it depends only on the cell and not on the electrolyte that we are using. Is this clear? So, this G star is what we call as the cell constant, and R of the solution conductivity of the cell is determined. Conductivity, kappa. Kappa is simply G star upon R. That is cell constant divided by the resistance that we measure, we are able to get the kappa, that is conductivity. Okay. So, anybody who has not liked as yet, go ahead and like it. Now, these are certain conductivities, these are conductors, here is insulators, and here are electrolytes. As you can very well understand that water is not actually a conductor. It should be something in between semiconductors. Now, what is the problem with direct current? For initial experiment, direct current was used, but this led to what is known as polarization. Now, this polarization term as such is not given in NCERT, but this polarization term is important because whenever we pass the direct current, some gases are liberated at the electrodes. Now, these gases form small bubbles on the surface of the electrode and drastically decrease its conductance. Now, this deposition of the gas particles, gas bubbles on the surface of the electrode is termed as polarization. Okay. Now, this polarization is going to drastically decrease the electrical conductance, and therefore, it affects the measurements. Clear? So, Kohlrausch suggested the use of a rapidly alternating current. The direction of the current is reversed about 500 to 1000 times per second. So, the polarization effects simply cancel each other. Could you give me the answer? Very few students are here. I believe 8 students are there. Prerna, I am going to tell you which tables are important. The table which I told you, the values of conduction, that is not important. You don't need to learn the resistance of each and every conductor. You don't need to learn even one. The value you don't need to learn. Now, answer. To measure conductivity of an electrolyte solution, the current used is. Answer. We have 8 students. I believe this I have done quite nicely and thoroughly. Just give me the answer so that I also understand that you are awake, not sleeping. Radhika, Priyanshu. Where are the others? Yes. It is always alternating current. Always a high frequency alternating current is used, as the use of direct current will release gases which will deposit on the surface of electrode and change its electrical conductance. The unit of cell constant is length inverse. That is the unit of cell constant. One thing you need to remember, that conductance is actually additive. It's like you have to transfer certain books from one library to another or one room to another. More is the number of students, more is the number of people carrying the books, more books are transferred per unit time. So, how many books are being transferred? It can be simply known by adding the books transferred by each person. In the same manner, how much charge is transferred, it can be obtained by adding the charge transferred by each particle. So, conductance is additive. It is added. Clear? So, total would be the conductance sum of all the ions and the conductance of water. Most often the conductance of water for the electrolytes and any other conductor is quite small, as we have already seen. Therefore, it is normally ignored or neglected, you can say. Is this clear? The conductance of water is often negligible in comparison to the conduction of all the ions. There is something called the word infinite dilution. See, I am telling you the terms at this moment. The term is infinite dilution. Infinite dilution is a concentration at which the electrolyte is completely dissociated, and there is no change in dissociation on further dilution. One thing is quite clear, that when we talk about the infinite dilution, this infinite dilution can be a practical term for the strong electrolytes. The strong electrolytes are completely dissociated. But if we talk about the weak electrolytes can never be completely dissociated. That is why they are weak electrolytes. So, this particular concept of infinite dilution does not work with the weak electrolytes. So, for weak electrolytes, infinite dilution is just a theoretical term. Strong electrolytes, they actually get the infinite dilution. Any confusion with that? At infinite dilution, all ions move absolute independent of each other. Each ion has its own electrical conductance, and total electrical conductance is the sum of the conductances of each individual ion. Now, that is what we know as the Kohlrausch law of independent migration of ions. That is, at infinite dilution, each electrolyte, each ion is moving independent of any other. Ananya, example of infinite dilution, let us say 0.01 molar solution of potassium chloride at the normal temperature. That can be considered as infinite dilution, because potassium chloride at that particular concentration is going to be completely dissociated. Is it clear? But when we talk about the weak electrolyte like acetic acid, that is not going to be completely dissociated at even 0.01 molar concentration. So, for that we cannot talk about infinite dilution. Clear? So, what is the unit of conductivity? Oh, resistance of a decimolar solution between two electrodes 0.02 meters apart and 0.004 meters square in area was found to be 50 ohms. specific conductance kappa is? Can you give me the value of specific conductance? Acetic acid is not dissociated completely, Priyanshu. It's only partially dissociated. It's a weak electrolyte. What is the specific conductance? Now we have length 0.02, resistance is 50, area is 0.0004. So here it goes 1, here it goes 2, and 1, 2, 1, 2. So it becomes 1 by 50 into 0.02. So here it becomes what? 1. Any confusions here? That's the answer. We are going to talk about molar conductance, equivalent conductance. We have just talked about the specific conductance. Today we are going to talk about molar conductance and the rest of the conductance in the next class. So we have already started our sessions. At 2 p.m. you have botany with Swati Batra ma'am. At 3 p.m. you have zoology with Dr. Sachin Kapur. And at 4 p.m. you have chemistry with me. That's Anoop Vashishtha. Clear? Join with us on t.me/NEET Elixir. That is our channel. Join with the Telegram channel so that you can get all the information here. NEET UG subscription, NEET UG subscription. This is, you can join with us. Go ahead with the subscription, and first of all you need to download the Unacademy app. Today we have the special class at 5:30 p.m. For that you need to download the Unacademy app, join it using the code AVLIVE, and let's have the quiz on solution. This is the address, unacademy.com/Anoop Vashishtha. You need to follow me so that you can get the information about all the classes that I am doing. Subscribe to the channel NEET Elixir by Unacademy for the best live classes. Like, share, subscribe and comment. Thank you. We are going to meet at 5:30 in the special class. Bye-bye. Take care.